advanced gallium nitride compact modeling for efficient RF power amplifier, and which is designed by Dr. Yogesh Singh Chauhan, and Dr. Nagaditya Poluri, and Dr. Avinash Lagere. So before we start the presentations, I would like to give a short introductions about all our presenter. Dr. Yogesh Singh Chauhan is presently working as a professor at IIT Kanpur. He has developed several industry standard models, a well-known personality. He is involved in developing compact models for gallium nitride transistor, FinFET, nanosheet, and gate all-around FETs. He is a fellow of IEEE and Indian National Academy of Engineering. He has published more than 400 papers in the international journals and conferences, and he has served as a technical program committee member for several IEEE international conferences. Moving to the our next speaker, Nagaditya Poluri. He is presently working as assistant professor at EE department, IIT Kanpur. He received his dual degree BTech and MTech in electronics and communication engineering from Indian Institute of Technology, Roorkee in 2013. He worked as a network consultant engineering in Cisco for a year, and then followed by data test engineer at Qualcomm at Hyderabad. He received his PhD degree from University of Sheffield. Our third presenter is Dr. Avinash Lagere. He has received a master's degree in electronics and communications from Indian Institute of Information Technology, Jabalpur in 2015. He received his PhD in electrical engineering from Indian Institute of Technology, Delhi in 2018. He is currently working as assistant professor of electrical engineering with the Indian Institute of Technology, Kanpur. He has worked as a member of technical staff at Global Foundry, Bangalore, where he has involved in developing SPICE model for 28 nanometer, 22 nanometer, and 12 nanometer advanced node devices. His research focus is on developing industry standard compact models for advanced CMOS, SOI, and RF devices and circuits. With this, I would like to invite Professor Yogesh Singh Chauhan to come here and start the presentation.
Hello. Yeah, thank you for the introduction. It's pleasure to be in the VLSI Design again. I'm going to discuss and talk about something which is not really opposite to silicon. So it's not silicon, it's something, a new material, gallium nitride, nowadays a hot topic. Also, especially if you look the gallium nitride, it is being pursued in two directions. One is the power electronics, other one is the RF. So in fact, power electronics market is much bigger than RF. Close to, it will be $10 billion versus what we are talking about, the RF, which is still at the nascent stage, but quite promising already in the market. You will find the chargers using GaN already in the market. So this is something we at IIT Kanpur, our group, we work all the way from measurements to compact modeling to the PDK and finally ship it to customers. So at IIT Kanpur, we are doing it for all different types of devices. I'm also proud to say that at IIT Kanpur, we are developing industry standard models, and more or less all the circuit designs you are doing, any industry, you will find IIT Kanpur name. So that's what we are doing. We have here three parts. One will be on the device physics, which is just giving you or trying to give you back what you read in your undergraduate. Then the compact modeling part, and then the RF amplifier part. So I will pass first to Avinash Lagere. He will cover the part 1. I will cover the part 2, and third part will be covered by Nagadit. So that's the introduction. Now let Avinash go through it.
nicely giving the introduction and providing the motivation that why we should actually pursue for the something which is not silicon, but it is a different and kind of getting a lot of attraction in the market and the industry. Okay, like as Professor Yogesh said, that we will be going to the multiple topics, and what we are going to do is actually we are going to follow the bottom-up approach. So before you actually develop any technology, the first thing you would like to know is that what is actually that material. When you make that material into the device, how the device works. And that is what my focus of this talk today. So without any further delay, so we are actually going to cover 3 different things under the device physics. That the first thing that we would like to see that where is the RF GaN market. So we look some of the numbers, some of the areas where the GaN market or let's say the GaN devices are getting a lot of attraction. Then the second thing we'll go into that, we'll start from the material device physics, and then we'll try to develop a GaN HAM device which can, and then we would like to see that how actually it operates. So like as we know that the India is actually in the like an innovation stage. We have already like looking at the 5G spectrum, and what we are doing is actually looking for that what is beyond 5G. Okay, it turns out to be that if you look beyond 5G, and if you're talking about like the 6G applications and all, RF GaN is actually a very attractive choice. If you look the different domains like telecom, defense, satcom and others, if we look the market anticipation, that what we have in 2023 is like around $1.1 billion business. And by 2029, that business is actually going to be around 2 times, okay, which is a huge attraction. And you will see like many innovation what we are doing and the strategy what India is also following, that's also having a lot of push about this market. Now, we will actually do a first comparison of our gallium nitride material with the commercial available silicon carbide device. So there are 2 key factors which actually makes GaN very attractive solution. One is like the critical electric field. If you compare the critical electric field of the GaN material compared to the silicon and silicon carbide, that actually gives you that you can operate the gallium nitride weight devices at a high power. At the same time, if you look that velocity saturation number, it's pretty high compared to the silicon and silicon carbide. And that is where that not only you can have a higher breakdown voltage or let's say the higher power capability of the driving, but at the same time you can also get the higher performance. So what is the consequence? So if we look into this picture, that what we are talking about in sub 6 gigahertz application, where we are having a lot of cellular devices operating like below 6 gigahertz and all, we definitely have a lot of players. But if you are talking about the beyond 6G, we don't have sufficient players. One of the reasons is that these materials are like silicon, silicon carbide are limited by their inherent constraint. And that is where the gallium nitride based devices are going to play a very key role. Okay? And that's why that when we are talking about the gigahertz frequency range or at high power level, then what we would like to see is actually how these GaN devices can be utilized for a cellular application. Now, if you look in terms of the application wise, so this is what we, a simple or simplistic way of the application, that this is like a pictorial way of a transceiver design. If you look into the transceiver, there are multiple actually important parts. One is actually like a power amplifier. So typically we use like a LDMOS devices to make the power amplifier. However, as I said, these LDMOS devices are either based on the silicon or silicon carbide. They may not be able to operate at high power. So the gallium nitride can be the one possible solution. Similarly, if you talk about the LNA, where the gallium arsenide weight devices are very, very attractive solution. So there are a couple of research and couple of industries are looking at how to design the gallium nitride based LNA. At the same time, if you look which connects to your transceiver, the transmitter and the receiver side, to the antenna, which is actually a switch. So because the switch also has to be very much it has to have a less loss and all. So gallium nitride can also be a potential solution to replace the SOI kind of a devices. Now, before I move to the gallium nitride based device, I will briefly talk about the gallium nitride material itself, and we will look into some of the properties that why gallium nitride is different compared to the silicon. So if you look to this periodic table, so your gallium is actually like a group 3 material, whereas your nitrogen is actually a group 5 material. So it's like a compound semiconductor. Now, if you look the crystal structure is like a Woodgite crystal structure. Now, typically gallium nitride is actually available in a 2 phase. One is actually called as a gallium phase and another is actually is the nitrogen phase. Now, depending upon that the phase material you can distinguish whether it's a gallium and the nitride phase. In general, what we actually use for our application is actually the gallium phase material. The reason why gallium nitride is actually different from silicon is actually that what you have is actually the gallium and the nitrogen. Okay. Now, both are actually having a very high difference in the electronegativity, and because of this difference in the electronegativity, what you have is actually like a polar bond, and that polar bonds actually leads to this internal electric field, and because of this internal electric field, you have some kind of a called as a spontaneous polarization. Don't worry about this spontaneous polarization, but it has a very big advantage in comparison to the silicon. So, I'll let you know what actually that advantage, but what you can do is actually by playing with the arrangement of the atoms, you can actually tune this spontaneous polarization value. Now, these are the different commercially available spontaneous polarized value for a different kind of a third 5 material. If you look in terms of like when it comes to the designing or like a fabricating a device, so the most promisable or let's say the favorable is actually like a AlGaN-GaN heterostructure. Now, there are 2 very key important things one has to follow. One is actually like when you make a heterostructure, the lattice mismatch should not be very bigger. It turns out to be that if you have a big difference in the lattice constant, it can lead to the defects, as that can actually make your device defective. Second thing is that you want to have a big band gap discontinuity, so you can actually hold the electrons into the potential ball, so they can be used for the thermionic or let's say for the transport application. So, these are the 2 constraints. Now, by changing the mole fraction of the aluminum, you can actually get the multiple aluminum gallium nitride with material. And the simple thing is that we actually use some kind of a linear interpolation in order to derive the property of a AlGaN material by just changing the X value. Okay. If you see in terms of the band structure, which is actually a very basic thing, so it turns out to be that for the AlGaN-GaN system, it's actually a type 1 band gap. What you have is actually like this is actually when the materials are not in contact. Okay, when you actually make this in a contact, they will be you have to follow certain device physics in order to derive that the band diagram in the thermal equilibrium state. One good thing that what we have already seen is actually you have a spontaneous polarization, but the moment you grow the AlGaN on top of GaN, because of the stress, you also have another polarization which is actually called as a piezoelectric polarization. Now, we will see later that by finding out that what is the total polarization, you can have some kind of a called as a charge density. Now, just to give you that some picture that how typically the piezoelectric polarization has been calculated. So, this is not something like people come up with like a mathematical equation, it is like a more material related. So, it actually depends on the several things like what is the lattice constant, what is the piezoelectric constant, and what are the elastic constant. And by varying the mole fraction of the aluminum, you can actually achieve a different kind of a piezoelectric polarization value. Now, so we'll start going to that how to build the device. So, as I mentioned that if you have a polarization like piezoelectric and the spontaneous polarization, by finding out the gradient between the polarization, you can actually have a charge, okay, which is very, very different compared to the silicon material. Now, this is actually the situation when the AlGaN and GaN are far from each other. The moment you actually grow the AlGaN on top of GaN, so what we do is actually we try to find out what is that gradient, the top layer versus the bottom layer, and it turns out to be that if you're using a gallium nitride as a gallium phase, and on top of that if you deposit or let's say grow the AlGaN, what you have at the interface is actually the positive charge. Now, you can simply see that now since you have a positive charge, the later when you have like electrons in the system, so those electrons will start attracting to this positive charge. And that is actually makes the gallium nitride or the L-GaN, GaN-based heterostructure is different from silicon. So what you see actually, without any conventional doping method like ion implantation and diffusion, you actually have electrons which are freely available for the conduction. And that's how actually we get that these gallium nitride based devices does not require any doping. And that is actually saves not only your makes your fabrication process simpler, but also reduce the thermal budget a lot. Now, I would like to show you, this is what we call as a two-dimensional gas, that what you have is actually that at the L-GaN interface, what you have is actually some kind of a potential barrier, and these are the electrons are actually attracted because of the positive polarization charge. Now, if you actually look into the dependency of how it depends on that different factors, so by modulating the thickness of the L-GaN, by playing with the potential barrier between L-GaN and the GaN, which is a Schottky based device, you can actually have a different kind of electron concentration. So just for your example, that if you actually increase the thickness of the L-GaN material, you can actually use this equation, which is actually derived by using the Poisson law and the Gauss law. So if you actually use and solve this Poisson law and the Gauss law across the band diagram, you can actually derive this, what the electron concentration in the 2-die. Now, so now we have some kind of understanding of what is gallium nitride, why is it so different compared to the silicon. We can now build a device. So what you have here is actually like a typical device, which is again like a 4-terminal device. Now the difference is actually is the typically the gallium nitride HAMT is actually like a normally on device. As I have mentioned that because of the GaN, L-GaN and GaN interface, you have a positive polarization charge, and that positive polarization leads to the electron. So you already have a conduction path. So the moment actually you put a bias across this device, you actually get to start seeing the conduction. Okay. Now another difference is actually that if you look at conventional CMOS devices or the bulk devices, the gallium nitride devices are having a multiple layers. This is actually in order to make it thermally and mechanically stable. I can quickly go through that what is actually the purpose of these different layers. So just for saving the time, so if we just talk about these are like a field plates, which is like a source and the gate field plate and all. These are typically used for the power electronic device in order to boost the breakdown voltage. Passivation layers are typically used to in order to make those field plates. Similarly, this is actually where your main device operation is happening, and the substrate, which is very, very important, and you will see not only in the literature but the industries are also looking what is the perfect substrate material. So it turns out to be that depending upon the substrate, you can have actually the multiple, or let's say you can modulate the electrical properties. So in general, like what we are actually looking for the gallium nitride on the silicon wafer, as we know that the silicon is available in the majority. So that is actually the one of the go-through choice for the industry also, that to develop the GaN-based devices on silicon wafer. But there are some of the industries, or let's say some of the researchers are also looking into the gallium nitride on gallium nitride based wafer, or gallium nitride on silicon carbide is also there. But as I mentioned that by changing the substrate material, you can have a different kind of a properties, and based on your application, you can choose the perfect substrate material. If we talk about the device operation, as I mentioned that this is what the device looks like when you don't have any bias across on the gate and the drain. The moment you put the bias on the gate and the drain, so you will start seeing some kind of a conduction, so your device will turn on. Now, in order to make this device off, since it's a normally off device, normally on device, so you have to put let's say the gate voltage such a way that it has a voltage less than the threshold voltage. So what you do is actually you deplete the electrons under the interface of this gate. So as a result, the path will broken, so there will not be any conduction. However, if you let's say that if you have a VG less than VTH, at the same time if you put a very high VDS, so what you see is actually the depletion region will again start extending toward the drain side. So you have a complete this called as like a blocking mode. Okay. If you see in terms of the characteristic, very much similar to like a MOSFET. However, there is a very much or one precaution you have to take. What you have is actually like a Schottky gate. Okay, so that actually forms a one Schottky diode between gate and source. So let's say if you have a voltage such a way that it has a higher voltage than the Schottky potential of the diode. Okay, what you have is actually this diode between gate and source will turn on. So rather than the current which is flowing between drain and source, you have a current actually between the gate and the source. As a result, if you are actually operating the VGS greater than the V Schottky, you suddenly start seeing a drop in the current. So this is actually like you can say is like a boundary condition in order to operate the VG. Okay, I think so. This is all about the device physics we have. Since now we have a basic understanding of the how the device works, what is the GaN material. I think so we have a perfect base that to now start looking into that how we can use this characteristic to develop the compact model. So I would like to invite Professor Yogesh to take it for the next part. Yeah.
Come again.
So
that's to block the electric field.
Yes.
You want to have much higher drain voltages. So there is no point in having this length larger. You want to make it very small. In fact, both of these you want to make close to 0. Both of these, you know, beyond gate. But you need to have that region so that that can sustain the electric field.
Yeah.
Thanks, Avinash. Okay, so now let me go into the compact modeling part. So those who are not familiar with compact modeling, you would have used or you might have heard about the PDK, process design kit. There you, if you see, once you have or your foundry has already made a beautiful device, you would like to then pass it to the designer. And the medium of information exchange is the PDK or compact model. So it should capture all the device physics, including the layout and everything, effects in the PDK. So core is the compact model part, and then you keep on adding all these things. So there are a lot of challenges in compact modeling. When we work on it, we start from the materials, like this is different material, silicon is different material, you have all these interfaces. So you need to keep into account all those things. Then the physics part, as you know, you have seen there is a quantum well, how many subbands you have to take. So all that quantum mechanics transport has to be taken into account. Then you have to solve the equations, those you have to solve by hand and make sure it works. So that is where you need to have a lot of information about not just mathematics but also some computer science. And finally, we need to remember that at the end it's the designer who is going to use. So don't forget what he or she wants, that's something you have to satisfy. So if it's the speed, accuracy, those you have to make sure that you are satisfying. So there are different classes of compact models. I'm talking about GaN, but it is true for any compact model, any device. There is one which is table based. When you have a new device where you don't have any compact model, just do the measurements, use that for doing the circuit simulation. Another is empirical, do the curve fitting using any function which it can fit, and then you can use that. The third one is the physics based model, and there are multiple approaches, threshold voltage based like BSIM4, BSIM3, those are threshold voltage. Surface potential based, our ASM GaN-HEMT model or the PSP model for MOSFET, and then there is a charge based model, this is from the MIT. So our model is this advanced SPICE model for GaN-HEMT. It is called ASM HEMT, this is the website. This became industry standard in 2018, and the first version is available here, but rest of the versions are not available online, but if you are interested, you can write to me. So what we have in the model, we have the solution of Schrodinger and Poisson equations, which gives us the 2DEG charge density, surface potential. Then once we have this information, we use it for the transport. So we have surface potential based current and charge model, which in turn gives the current, capacitance, charge, and then we add all the other effects. Then we also have all the higher order effects which are observed in this device or any other device like noise, trapping, self-heating, field plate. With all this, finally you can do all the simulations, whatever you are interested, whether it's the power electronics or the RF or the load pull, harmonic balance, whatever you want to do. So once we have this core model using the mathematical equations, then we add all these sub-modules on top of this to ensure that we are capturing all the device physics in there. We cannot just use the TCAD model because that's very expensive in terms of speed. So we have to do this in an ad hoc manner, that whatever extra effect or another effect you see, add it in the device or add it in the model. So you can see here these mobility degradation, channel length modulation, debel, velocity saturation, all these are then added on top of this, and this entire package is then now a compact model. These are some of the main parameters which are very similar to the BSIM models which are there in the MOSFET. So you have, for example, the threshold, this is called the threshold voltage, subthreshold slope degradation, debel parameters, and saturation velocity, etc. This is just showing you the equation of the current in terms of surface potential. So going to the compact model methodology, once we receive a wafer from industry, or it can be on wafer device or it could be the package device. We take it to the characterization lab. This is the characterization lab. We do the measurements, and then in parallel, we have our ASM HEMT model, which is already available in the EDA tools. So all the major simulators, they have this model. Match the model with the measurement. You are seeing this typical characteristic, and then finally we can do the circuit design. And at IIT Kanpur, we are doing all of these activities, including all the way from measurements up to the circuit design. This is the device characterization and modeling flow. So once we have the geometry information of the device, we do the device characterization, DC, CV, pulsed IV, S parameter, load pull, and then we analyze the data, do the parameter extraction to fit the device measurement, and then it is packaged in the PDK, and finally it goes into the circuit simulation. And this is just showing the RF extraction methodology. I will come to that. So this is the characterization lab we have at IIT Kanpur, where we have all the pulsed IV, load pull, tuner, noise figure analyzer, everything whatever is required for the device to circuit characterization. And we are providing PDK services to companies worldwide, and we get the wafer, and finally we ship the PDK. This is extraction flow. So as I already said, you start with the geometry information, go to the main parameters, extract the mobility, velocity, saturation, etc. Go to the IDVD characteristic, then look into the temperature characteristic, because normally the first you would be doing it for the room temperature, and then we will be going for the other temperatures. So this I have to go a little fast, but this is the extraction flow. What we see that it starts with the subthreshold characteristic, then it goes into the above threshold characteristic. So you can see here it's the mobility. You have here this is the IDVD velocity saturation. Again, this is also for the access region equations, and then finally the self-heating parameter. So finally the black and these dot, you can see they are matching it perfectly. And note that these measurements are not being done because of the power handling limit. So you cannot do these measurements in a normal DC mode. You have to go for the pulsed mode if you want to go to the higher VDS. Extraction from IDVGS, so I already highlighted. This is, for example, this is the debel for different drain voltages here, right? You are seeing here. And this is, in this region is where we will be extracting the mobility parameters. And then for the IDS, VDS, mainly it will be the velocity saturation. You might have to play with the mobility degradation parameter. Access region parameters are very important, because as there was a question, you have these big access regions, one on the source side, another one on the drain side. So you have to play with these parameters to match the characteristic. And then the 2D density parameters, saturation velocity, low field mobility, etc. So this is the GaN HEMT. You can see that This is the gate under the gate region. This is the LSG or source to gate distance, drain to gate distance, and the device is always asymmetric because you, depending on the how much the drain voltage will be applied, this voltage will be, this length will be larger. Since these devices are seeing quite high voltages going into, you know, even 28 volt or more, this region will start seeing the velocity saturation here. When you have velocity saturation, even if you increase the voltage, current is not going to increase. So in turn, you can say the resistance which you are seeing, if I say R equal to V by I am increasing V, but I is not increasing, saying that R is increasing. So you have a non-linear resistance, and we need to account the velocity saturation in this RDS model. So that's why this equation is showing you the inclusion of velocity saturation in the RD and RS. And you can see here these high access region resistances. Then you start seeing these bunching of different IDVD curves for different gate voltage. Now there is no more increase in current even if we are increasing the gate voltage. Same even on the reverse side. This device you can do both sides. So you can apply the voltage on the drain or also apply the on the source. So you can see here same is happening in this side also. So this good fitting needs a very good physics based model, and that's why we have to take care of each and every region carefully and making still it computationally efficient so that circuit designer doesn't need to run it for hours. Second important thing is self-heating, because there is a huge IV or power drop. All of that is converting in the form of heat. So that heat is going to produce what is called self-heating. As the temperature is rising, everything will change. Your mobility will change, your resistance will change. All of that has to be modeled properly. So we have this self-heating network, which is then which is used in the model, and you can see here this sharp drop in this IDVS VDS characteristic that's coming from the self-heating. So this is very important to model in this device. So then the next is the temperature scaling. See, once we have done the modeling at room temperature, this device is going to be operated from anywhere in the negative, minus 40 degrees C to even 150 degrees Celsius, right? So then we look and model, we have already the temperature parameters in the model. We tune these parameters to fit the characteristics all the way from low temperature to high temperature. You can see here, this is the 100 degrees Celsius here. This one, this is minus 20 degrees Celsius. Here 100 degrees Celsius IDVG and minus 20 degrees C IDVG. Then we also have the geometrical scaling, because we want to make sure whenever this model is there, it works for different widths and LSG, LDG, access region length. So all of that is already captured in the model. You can see L and W here in different equations, all of that. And these are long mathematical equations which then once implemented, normally you do not see them as a circuit designer, but behind this model you see there is a lot of physics and mathematics. Okay, so now let me go to the parameter extraction for RF. This is the model or PDK which you are seeing. You need to model the manifolds for this device, gate, drain and source manifold. It's a 3-step. One, de-embed these manifolds, extract the intrinsic core model, this one, using low frequency Y parameters, and then extract these inductances for the using the high frequency parameter. You can see here, that's the device layout, a typical device layout. These devices have different variety of, let's say, ways to make. Sometimes you have connection through via, sometimes you have through the air bridges, etc. So this is here showing the showing through the via. So in RF, most important is that whatever you are measuring, is that your real device characteristic or something else? That's the major problem. And for that, we need to do the de-embedding. So if you see this, this is your device, these are your pads, and then you have long cables. Question is, whatever you measured, it measured everything up to this. So you really don't have the device characteristic. To get those, what you should do is that remove all this, whatever extra you are doing. So we need to have these on-wafer test structures to calibrate out these things. This is a typical, for example, showing you the circuit demonstration, what you have, and now we need the structures. So you should have DUT, then you have open, and then you have source, open source de-embedding. And then this is, you can see the circuit representation, you are doing the open measurements, you are measuring these Y parameters, you are measuring these Z parameters, and then you can easily do this maths to actually see your DUT S parameters. I already told you the manifolds. It's very important to do the measurements of manifold and then model it. So we use this. Either you can have a direct S2P file, which is if it is available from the vendor or from the foundry. Otherwise, you can do the matching of these measurements from the using this simple transmission line representation, and then you can see this is all working up to. Here the measurement is up to, I think, 50 gigahertz or so, roughly. And you can easily write these equations, Y parameter, in terms of the capacitances and resistances or the channel region. Then it all helps us to extract the different things at versus frequency, capacitance, or real part, imaginary part, etc. So this is all showing you all these equations that you can actually plot these directly using the Y parameters. So here I am showing you, note that it's not really a capacitance, it's coming from the imaginary part of Y parameter. So this is CGS, real part of this will be Y, ID, VG. So Y21, right? This is CGD, and GDS, real part of Y22. All these plotted versus frequency here, and you can see a very good matching with the measurement data. And then this is the bus inductance fitting. I told you that you also need to account those one, and you can see that all of these from real and imaginary parts, there are even these resonant peaks due to these interaction of inductances with the intrinsic device capacitance. So that gives you these resonant peaks. And this is the plot showing you S11 and S22, S12 and S21 for two different voltages here. And then we go to the large signal harmonic balance. That's the most important, because unless for RF power amplifier designer, unless he sees this, or he or she, doesn't care about anything about your model. So it is important that we model the P out versus P in. You can see that output power versus input power and gain plotted here, and the match here, right, including the gain compression region here, showing you here one for VDS 5 volt, 10 volt, and this is the power added efficiency, PAE and P out and gain, showing here again for different different VDS. You can now, once you have done all this model, you can actually simulate this model to analyze what is happening actually. So you can see how the drain to source voltage will vary in this device, how the drain current and drain voltage is, and how the load line is, where is the load line. So all of that is now giving you an opportunity to analyze and design your amplifier, whatever you want to do in whatever region you want to do. And here, for example, I am showing you the validation, real and imaginary loads. So it's very important, because what you are seeing that we are having pretty good accuracy in predicting the maxima of P out and PE. See, when RF power designer, PA designer, he will be always optimizing the P out and PAE, right? And what we are saying that now you have the handle, now a PA designer, let him or her choose where he wants to put or bias his device. And this is the load pull simulation here using ASM HEMT. So we do all this, our model is here. All of these are in the ADS, and then you can see the load pull contours here, P out and PAE contours here versus measurement. And I can tell you those who are RF power designers, especially working in GaN, if they are seeing this, they will be very happy that can your model really predict this? So we are regularly doing it. And as I said, all the measurements we are doing, and then all the model overlapping also we are doing. Okay, just one or two what other things we are doing. So GaN, the switch, currently you will see it's a SOI switch normally in the transceiver. RF switch using GaN is something which we have also started working few years ago with the foundries, and we have been very successful now in doing the GaN switch. It's something which you will see in next few years. You will see it in the market. This is here showing you a dual gate depletion mode SPST. You have actually, although I am showing here VG1, VG2, both of them are tied here. So they are both connected together. This is the device layout and measurement setup shown. This is the equivalent circuit. We already published all of this work. If you are interested, you can look at it. And here I am showing you the validation. So IDS, VDS, small signal parameters and isolation, and also the insertion loss. So that's something coming from the actual measurements of the SOIs of the GaN switch. And another thing which is more like a research stage, I would say, is the FinHEMT. These devices, if you make it like a fin, you start seeing a weird characteristic. We have modeled those, and you can see that there are 2 threshold voltage in these devices. We worked on also the small signal validation, and this is still work in progress in terms, it's not yet going to come to industry, but there is a lot of hope. Another thing nowadays, quantum computing, all of you would have heard, a lot of buzz is there. Our group is working on cryogenic MOSFET modeling. Here I am showing you the GaN HEMT modeling at cryogenic temperatures. So here you can see that all the difference, threshold voltage versus temperature, IDS, VGS, IDS, VGS for different temperatures, going up to, I think this is shown here, 10K. So up to 10 Kelvin, you can see the model is actually working, this model. Come again? No, it's everything is measured. Whatever I am showing, the data means measured. Yes, yes, yeah, even lower than that, yeah. Okay, so now let's go to the third part. Nagaditya will cover the RF power amplifier.
Hello? Okay. Yeah, thank you. Till now we have seen what a GaN device is, how is it made, and what is required for the modeling the device. Now I will take till now the approach was been from a bottom up approach, like what my colleague has told. They have started from the material and went up to the model. Now I will be taking a different approach where I will be covering coming from the top, from the application point of view to the device, amplifier level. Now, okay, so first this is where I will be covering the top down approach. So I will show you where the RFPS are used in the context of a wireless communication system. Okay, so now this is a block diagram of a wireless network. So there are, I tried to make it as simple as possible, so just a very top overview. Now, okay. Now, so this entire thing is a network. And what we will try to understand how this works, we will try and send some very simple message, hi, and from a WhatsApp, and try and send it from this mobile to this mobile. The instant you type hi, it is on a application layer. Then go to the presentation layer, session layer, transport layer, network layer, then data link layer, then finally the physical layer. Now each of these layers will keep on adding some identification to itself. For example, many of you must have heard IP. That would be at the network layer, and this component, routers would be working at that level. Now, so once in this topic, we would be talking more at a physical layer. And in the physical layer, we will be not covering most of this one. We will be talking the physical layer at a RF, wherever there is a wireless link, that is between cell phone to a base station and base station to the cell phone. In the physical layer, we have something called, related to the RF level, there is something called RF transceivers. So now your message is at a base band. It is simply a string of bits, 1010, some string is there. Now we will have some block which will modulate it and upconvert it. When I say this block, what it essentially does is, in a RF signal, you have you can think of it as a sinusoidal. And on that, you have 3 parameters. One is amplitude, frequency, and phase. So this block, this essentially does is, takes your baseband data and modify amplitude or phase or frequency in such a way that it can be read by someone receiving it, that's receiving that signal. So that's all this block does. Okay, I oversimplified it, but there are a lot of things inside, but that is basically the overview, top overview. Now, that signal will be amplified so that you have, it can be received at a certain level by your base station. Because over the wireless link, you have a lot of losses. So to accommodate that, we will be having, we need to amplify it before we send it to an antenna. Now, similarly, when we receive, so this is received by the base station. Now it will route through all this. All that information is already present at different layers. Now at the base station, and base station will again convert it to RF and send it to another mobile. Now that signal is received, and we will again amplify it, because the signal would have lost some power, and again down convert. This is where you are decoding the information from your RF signal. Okay, now throughout in this entire thing, we will be discussing, our focus of this topic is on a RF power amplifiers. Now why RF power amplifiers is important to study is because this is the data I have collected from 4 different journal papers. What this shows is, in a wireless network, nearly 57% of your power is consumed by the base station itself, and out of this 57%, nearly 60%, 30 to 67% is being consumed by just one component, that is RF power amplifier. So you can see, and now you see how much a wireless network energy is consumed in a year. It is estimated to be 100 terawatt hour per year. So out of this, you can calculate how much energy is being consumed by just one component. So this is how critical the PA design is. That is where one of the major challenges is, how to make sure that these PAs operate at a highest possible efficiency. Okay. Now this is what has been happening till now, and in 6G we are looking at several new application areas. So beamforming and antenna arrays, portion of it has already been implemented as a part of 5G, but here the talks is talking about beamforming at a very massive scale, like in hundreds or thousands of arrays. And then millimeter wave communication, this has been tried in 5G as well, but didn't take off that much. But I think this in 6G, there is still an hope that it will pick up. Now, dual functioning radar and communication. Radar, we are already seeing an application in a collision avoidance in a vehicle, autonomous vehicles. But now the thing is, how can we use the same radar for both communication as well as radar applications? That is the main idea. Now, satellite communication link. I think we have already seen some application of it. Starlink is one of the example, and it has already been making revenue. And then integrated access and backhaul. Now, here in the previous link, I have shown only one wireless link between base station and mobile, but there can be this, whatever happens within the network can also be on a wireless case. That is what is referred as backhaul. And Ericsson's survey shows that nearly 5 to 10% of the wide network are being used at a V band and mostly at a W band in a backhaul. So there is still a lot of application. Now there is like, I may not be overstating if I say every antenna is preceded by a power amplifier. So now here you can see how many antennas will be used and how many power amplifiers will be used. So it definitely makes the power amplifiers designer happy, because we have a lot of challenges to tackle. Now that brings us to the basics of power amplifier. Now I'm not sure how many of you work in power amplifiers. Quick show of hands. Okay, quite a few. So okay, for those who are working, I say this is like a overview. And for those who are not, I hope I do a better job in explaining things better, understand how an amplifier works. So this is at a very basic level. Now what an amplifier does, you have a signal at a certain amplitude, it just increases its amplitude. Now what is the parameter corresponding to that? It is the gain. Gain, it is ratio of output power divided by your input power. Now, is the circuit generating power? No. It is consuming some power from your DC supply to make this increase in the amplitude. Now, can the DC power is equal to output minus input? That means whatever being consumed by the PA is entirely used for amplifying the signal? No. That means this equality will never be the case. So we have another parameter called how much is the power P out minus P in, P out minus P in divided by PDC. That means how much is being converted in RF, amplified in RF to the what is actually being consumed. So I have defined two parameters here, gain and efficiency. We will talk about these parameters in the next stages. Okay. Now before I move to the amplifiers design, I will quickly introduce S parameters. So you have a device. For this you bias, apply some gate and drain voltage. Now this one is a common source topology. I hope many of you will know it. So now it has become two-port device. Two ports, port 1 between gate and source, port 2 between drain and source. Now the way S parameters is defined is, you apply some A1 and A2. Can anybody guess what is A1 and A2? These are power waves. So essentially what we are simply doing is, we are simply applying some very small signal, and some of it would be reflected at the input port, some of it would be going into the, getting to the port, second output port. Now we will take what is being reflected as, is defined as S11, what is being transmitted as S21, and we will do the same thing on the other end. We will apply some very small signal, and some of it would be reflected, some of it would be coming out at the P1. So for that, the S parameters would be S12 and S22. Now you have calculated, you have a transistor, you have bias data, and you calculated its S parameters. Now it is generally not true that these devices will directly be matched to your source impedance and load impedance. In RF domain, we generally, the source and load impedances are 50 ohm. So these transistors are not generally matched. So we need additional networks referred as matching networks at the input and output to make sure that at this port the device is the proper impedance for the maximum power transfer, and at the load also, source also sees a similar impedance at this network as well. So now many of you may have heard the maximum power transfer theorem. That means we would expect gamma s to be conjugate of gamma 1 for the maximum power transfer, right? Similarly, we can make gamma 2 should be conjugate of your gamma L, right? Now, if I put a conjugates everywhere, will it ensure that the power from here, maximum power would be delivered to your load? The answer is no. Why? Why? Because the S parameters are at, we are talking at a very small signal. So as Professor Yogesh has mentioned, we are looking at something at a large signal level, like a gains at a varying power levels. Now S parameters, they are at very small signal, small levels. Now there are other parameters, X parameters, which take that into consideration, but rather modeling is the major way where most of the amplifier designers rely on. Okay, now this is a very brief overview of what an amplifier contains. So it has, you have to bias your device. So you have DC supplies at gate and drain side. Then you have to present a proper impedance to your transistor so that you get a maximum amount of it. The impedance strategy could be either you maximize the power, efficiency, or gain. Now, then you have to design it consists of a matching network which makes sure that the maximum power is transferred from source to transistor and transistor to your load. Similarly, then you have to have some biasing circuit so that the RF power coming from here doesn't go leak into this your DC supply. Most of it goes to this one. Similarly, DC part is being delivered to this one, but not goes into this portion. Okay. Now, till now we have looked at the block diagram of an block level understanding of an PA. Now, I will in the next few slides, I will be explaining how a PA works. Now, for this, I will be taking this very ideal device, which doesn't exist. Now, the important thing is it has a very constant GM over between VGS and VGS sat. That is the assumption I am making, and there is no variation of the current with respect to the drain voltage as well. So this device is essentially acting like a voltage controlled current source. Now to this device I am applying at the input I am applying some sinusoidal whose amplitude is 1, same as from which is driving whose amplitude is 1 here 0.5 here. Now what would be the output? The output current would be also a sinusoidal, right? This is a voltage voltage control current source. So you apply a sinusoidal current, you are getting a sinusoidal sinusoidal voltage. You are getting a sinusoidal current. Now we connect a load to your voltage current source, which is R load. So since it is a resistive load, you will be, since the current flowing through your load is sinusoidal, you would also get a sinusoidal output. So this is this R load is our design parameter. So for this case, only thing we have to figure out is this R load. If we know this, we would have made sure this is our design parameter which is required for the amplifier design. Now, so till now you have seen how the amplifier is generating your current and voltages at your load. Now, how do I identify my maximum optimum R load? So for that, people use load line theory. So the idea is like you plot current versus voltage on this one. Now since, as you have seen, the current and voltage are sinusoidal and out of phase, you just get a straight line. Now what would be your slope of this line, it would be minus 1 by R load. So now by just looking at this, because just by looking at this, we can design one amplifier. For example, in this case, I am showing one example where the current swing is, it is not going to Imax. So this is a unoptimal condition, right? For an optimum condition, we want to deliver maximum power to your load. So that means we want to maximize both voltage as well as current swings. Here the voltage swing is the maximum. It is going from VDSQ to VNE, but it is not covering the entire current swing that is possible from this device. So now how do we identify our optimum load line? So we will just say we want to, the maximum current swing that is possible from this device is Imax, this much, which I have put the equation corresponding to that one, Imax by 2 plus this. This is the maximum current swing that is possible from this device. Now what is the maximum voltage swing that is possible from this device? It is this much, VDSQ minus VNE. Now corresponding equation would be this. Now all we have to do is take the ratio of your voltages here, VDSQ minus V0, we will get a optimum load, which will transfer maximum power to your load. Now alternatively, you can simply draw one line from this point, passing through these 2 points. If we know 2 points, we simply we can find the slope of it, and then that will be equal to minus 1 by R out. So just by looking at IV curves, we can preliminarily understand what would be your design impedance will be. Now for this device, you can estimate the efficiency as this. Now now to further improve your efficiency, what is generally done is you reduce your bias point. Now the way it is at the bias current is reduced, as a result your denominator is reducing. Efficiency is in the denominator you have a DC power. So that means by reducing your, moving your quiescent point to downwards, you are reducing your DC consumption, so efficiency improves. So based on the where you bias, there are several classes. These are all referred as reduced conduction classes. So they, now for these classes, it will not, the current would not be a sinusoidal as in the class A. It would be clipped, because for some portion of it, the voltage is going below the threshold. As a result, you will get some clipped waveform. Now, when the sinusoidal, if you are, once it is clipped, it is generating harmonics. So definitely a resistive load will not work, right? If you just pass that harmonics to that one, it is dissipating that power at a harmonic which is unwanted. So what is generally done is we use an LC filter to remove all the harmonics and only pass our fundamental to flow through your load, and where it is maximizing the output, where we are delivering our output power at a fundamental. Now I have already shown the load lines corresponding to all these classes, and you can see just by looking at the graphs, we can identify what would be, and from this load line theory, we would be able to graphically estimate what would be the load condition which is optimum for each of these classes. Now, if we do the analysis, even though current is getting clipped, we will be having, we will not be sacrificing any efficiency. At the same time, we would be, any output power, but we would be improving the efficiency without sacrificing the output power. So that is why generally most of the PS would be designed in this area where you get best of both output power as well as efficiency. Okay, till now I have introduced a very basic overview of an RF power amplifier. Now we will see why GaN, how GaN impacts the RF designers and RF power amplifiers. Now I would be, I would be more focused on the this breakdown voltage and those ones, how this increase over this will be beneficial for RF designers. So we have seen that output power is proportional to your VDSQ, and impedance which the load which you are calculating is also proportional to VDSQ, and efficiency is related like this. Now, if with the GaN devices, since breakdown voltage is higher, it gives an opportunity to increase the VDSQ, and we can design something like this. So once if the VDSQ is increased, definitely the output power will increase. It will improve the Z, the load. Why this increase having a higher load resistance is better? Because it is easier to match and reduce the losses in the matching network. But this increase in VDSQ doesn't directly result in an improvement in efficiency, because both the numerator as well as the denominator is increasing. So for that, RF designers use a harmonic manipulation. Just now we discussed that all the harmonics are being removed, is being shorted using a LC network. Now what I try to illustrate in this figure is, this is our fundamental component, which is this, which is purely sinusoidal. Now rather than filtering out your second harmonic, what we will do is we will present a capacitive or inductive load that will generate some if the current flows through an inductor or capacitor, it will be generating some additional voltage. Now if we can phase that additional voltage in such a way shown here. Now two things happen, like I have connected some load such that this minima of my second harmonic voltage, which is generated from the L or C, is in anti-phase when compared to this one. Now that will increase my minima as well as maxima. Now increasing the minima gives me an opportunity to increase the fundamental component of my load, fundamental component of this fundamental component as shown in here. So in this case, rather than going dashed line in the in a conventional case, I can increase this fundamental component by increasing the load seen by the transistor such a way that till the minima again reaches to the knee voltage of our device. So that means by using the harmonics which is shown in red, I was able to increase the fundamental component delivered to my load. Now as a byproduct, what I have also done is increase the maxima from 2 times VDSQ to 3 times VDSQ. That means having a higher breakdown voltage in a GaN gives me that flexibility to increase this and get a higher efficiency. That's how we can liaise the higher breakdown of voltage of GaN for improving the efficiency of an power amplifier. Now, in the previous slide, I have shown how harmonic manipulation can be used to improve the efficiency. In this one, here I have plotted a set of waveforms where the second harmonic is amplitude is adjusted in such a way that you get a set of waveforms like this. Now, all these waveforms, if you calculate, their efficiency is same. But the benefit I get is what you see here. In the previous case, I have to precisely select my fundamental and second harmonic loads in such a way that I get these waveforms. Now, I can select any of these impedances to improve my, to get the same efficiency. That means I can use, from a designer perspective, it will be beneficial in two cases. One, it will give a tolerance to your PA. because even if there is a mismatch from here, it will be any impedance can be used. Secondly, over a frequency, you can it is easier to match in this case, because with frequency, impedance of a matching network changes, and we can try and make sure that the frequency response of our impedance matching network lies in these impedances. So that from a design perspective, I'm getting two benefits. And here here you could see the voltage is also increased, magnitude of maximum of my voltage also increased from 2 times VDSQ to 3 times VDSQ. Here the benefit I would be getting is the increased design space. Now you can play the same game with the current as well. So you can reduce the current you can play with the second harmonic of your current in such a way that you reduce the overlap with the voltage and get the efficiency in theory up to 91%. Here also I am using 3 times VDSQ. So that is the advantages, and here I am showing some of the recently published data where I am comparing the CMOS, GaN, GAS and LDMOS, which are generally used for RF in RF applications. As you can see, GaN in this region it is able to deliver high output powers. 50 dBm is 100 watts, and this one is 100 watts and above, and also at a very high efficiency. You could see it is reaching near to 60 to 80% of efficiency in that high power levels. And this is where, this is the frequency ranges 2 to 6 gigahertz. And here you could see the GaN has done a very fantastic job in terms of achieving both the axes, both output power as well as the efficiency. And none of the semiconductor technology was able to match this. Now, this is the data for 6 to 20 gigahertz PS. Here also I am comparing, CMOS, GaN and gallium arsenide. You could observe that GaN was able to achieve high output powers, high saturated output powers, but efficiency it is still not able to match with gallium arsenide. Now I will be discussing very brief overview of how a GaN amplifier is designed. This one is, we have a foundry devices, we can do the measurements. We check whether the generally foundries have supplied models, and we compare them. Generally, they may not, they have discrepancy. That is where the models, that is where Kanpur is focusing on developing a very accurate models, which is where you have this measurement versus model is accurately matched. And if the foundry model doesn't match, then we have to rely on the measurements, but we can develop our own models. When it comes to the amplifier design procedure, you start with the specification, whether you want to maximize what is the output power, efficiency, gain. Then the select bias point, then identify the optimum impedances, then matching network. Then we have to iterate over a lot of this. If something iterative process is generally developed. In a recent publication, we tried to combine these two steps together using an algorithm. So I will show what is the conventional method where you are iterating over all these steps, and what our approach algorithm were able to do it. So this is the conventional design technique. In here I have already identified the optimum, the gate and drain bias, then found out the optimum design space, the impedances which result in optimum efficiency. Then we have to find a matching network which realizes this high which has impedances in this region. If we take the same matching network and optimize it, you will have two different matching conditions which I am shown here. It is the same matching network, you change the network values, you get this impedances and this impedances. The difference is, in one case you get a bandwidth of 400 megahertz. In other case, you get a bandwidth of 900 megahertz. It's the same matching network, different values. Here, we are matching the same impedances in these two cases using the same matching network topology. Here also, different matching network topology. The blue is this topology, green is this topology. Here also bandwidth varies. So you could see in a trial and error, it requires a repetitive process in identifying these two cases. It's like same network, if someone designs it gets certain bandwidth, someone else designs it gets a different thing. It depends on what is the optimization algorithm you used, or how you reached at those values. So that is a trial and error method. Using the algorithm, we designed this amplifier, and you could see most of the same power level amplifiers were lying below this line, and our work achieves both the high efficiency and operating at high frequency ranges. Now, I will briefly discuss what are the issues with GaN power amplifiers. So the main, it is previously covered in at the device level. There are two things. One is the trapping effect, which changes your drain current, which you can observe in two pulsing conditions. Same pulse you apply from different quiescent points, your drain current varies. Similarly, there is a heating effect because of which you see if you apply a pulse for a longer duration, you see a reduction in current. This is due to the self-heating, which is discussed in the previous part of this tutorial. Now, this next few slides, I will be using this as my DUT, and for the analysis perspective, I have divided into 3 clusters. The cluster 1 is where the RF signal is so small, it is not making much change in your bias point as shown in the black curve. Cluster 2 is where you have some signal, but it is still sinusoidal because the gate voltage is not going below your threshold voltage. Cluster 3 is the green one where you have a half sinusoidal kind of current, and cluster 4 is when you have it is near to saturation. Amplifier is near to saturation. Now, for this analysis, what I have done is I have applied a signal whose amplitude is varying with time. So here, this is what I have plotted is an envelope of that signal. So with time, its amplitude reaches this maximum peak envelope power and falls back. So it's like this is what the signal I have applied to a GaN amplifier. Now, in a cluster 1, where you have very small variation in cluster 1, you would see that amplifier gain is more or less flat. But for cluster 2 and cluster 3, we observed that when the signal is being applied and its amplitude is increasing from 0 to maximum, you have a gain near to 20, same as what you observe in this one. But for the reverse sweep, the gain reduces. So this is the forward sweep. We increase the amplitude, went to maximum, and in the reverse sweep, when we are reducing the amplitude, its gain is different. This is because of the trapping effects, which is in a GaN devices. Okay. Now, in addition to applying these varying amplitude signals, what I have done is I am observing what is the drain current consumed by this device. So I applied two signals consecutively like this. Increase the amplitude, reduce rate, increase the amplitude, reduce rate. Now, after removing the RF signal, the quiescent current has changed. You see, at the beginning, before the application of RF signal, it is near to 150 milliamp. Now, after removing your RF signal, it has become to a different value. The reason is because the trapped electrons still hasn't went back. They're still in this trapped state. So as a result, they act as additional voltage source and which is referred as a virtual gate, and as a result you see this one. So now when you apply a signal here, let's say you apply another signal at 70 microsecond, device is going to operate, amplifier is going to operate as it is biased at a different bias, different from what you are intended to use. Now what I have done is I have increased the time period of this signal. So now for the signal what you are seeing on this side, for this measurement what I have done is I have applied the signal for a duration T1. So 2 cycles of them, and for the second cycle I am measuring this. So note that here even though for the space I am showing 1 cycle, this measurement is for the, I applied, increased the signal amplitude, reduced it, increased it, reduced it. So for the second cycle I am doing this measurement. The second set of measurements, what I have done is I have increased the time duration of this application. So now it is a much slower signal. For this, for the second cycle, what I am observing is that even though cluster 1, if you remember, cluster 1 is just where the signal is very small, where there is no fluctuation in the bias current. Still we are seeing the reduction in the gain. In one case when T1 is nearly 2.5 microseconds, you have more or less flat gain. Whereas for the second one, you see a reduction in the gain. From the reduction you could see from measurements, nearly 3 dB reduction in the gain. So this we can attribute to the thermal effects, self-heating effects. So what in summary we have done is we have started with material level to all the PA level and design level. So we are open for questions. Any?
With this, we come to end of our tutorial. We would love to take questions anywhere from material to the circuits. Yeah, thank you. Yeah, please.
So we did not talk about stability analysis of the PAs. I just wanted to ask, I mean, we know there are small signal stability analysis, but in these kind of circuits, since we are dealing with, I mean, PA is a large signal. So how do you analyze for stability?
Okay, so small signal stability, as you know, K and mu is being used, but for high stability, we used Nyquist criteria and other things. That is more relevant when you are talking about very high power levels. And so there you have to look at K and mu will not be sufficient. There are other parameters we look at as well.
So can you tell me, like, what are those parameters?
So Nyquist stability criteria you must have heard.
Okay,
Yeah, right. So there is, you have poles on a left side or right side. Those kind of analysis have to be done. Okay.
So have you ever faced any issue with the stability with all of your circuits?
Generally ADS already has a very strong tools, like we use ADS and ANSYS to make sure that we take all the thermal as well as the electrical feedback, whatever loops that are being unintentionally arising into consideration, and we have a very good model for the device. So most of it is taken care of.
I would like to even add these devices, since these devices are operating in quite extremes. You sometimes even have a stability problem even during the measurements. So it's not easy. Sometimes it's very tricky to do even the device measurement. So we do face not just circuit but even device level measurements. There is a stability problem.
Any more question? Yeah.
Sir, in transient gain analysis, you have shown 3 diagrams. So which were giving gain is around 20 dB with the minus 3 dB variation, and you got the P out on x-axis as 15 dBm for one case and 30 dBm and 40 dBm another case. So will it affect any PAE variations, or how you have analyzed to maintain the constant gain?
Okay, so I am interested to do the PAE, but the current sensor which currently in the lab can't support that high change in the current. Okay. So that's limitation from the lab, but I would like to explore that.
Sure, sir, I'll work out. And another last question. The frequency analysis, when we have done, you have shown 1 to 10 gigahertz as one frequency variation on x-axis, and another place as 50 gigahertz also. So the total models were tested for less than 24 gigahertz or millimeter wave also.
Models, when we are developing, if we have the measurement data,
right,
or if we are able to measure,
correct,
we do it for the entire range. Okay. So the plots I have shown there, we are talking about 60 gigahertz.
Right.
When I say 60 gigahertz means really all the way from lowest frequency to the highest frequency. I'm 60 gigahertz. Right. So all the, let's say, usable frequency range we always cover.
Yeah. Sure. Thank you.
Yeah.
Thank you very much.
There is one more question, my last question.
If we can take it after having.
My last question and we cover.
Okay,
yeah,
sure.
we can.
One is a generic, specific question and a generic question. The specific question is the dibble direction. How the DIBL that we had spoken about.
Yeah.
So in silicon, it is easy to understand why the DIBL comes and where it comes. But
True.
here, there is no such junction getting formed. So where is that DIBL coming from? And
So that's a good question. I would say it's a more of nomenclature. There is an impact of drain voltage on the subthreshold characteristic or shift in the threshold voltage. These devices have a lot of different other problems like trapping and all that, even in the device level or in the barrier low. See, there is a barrier. It's other way around barrier. You are creating a depletion. It's not a junction, but you are creating a depletion. So it's like that. There is still, you can say, the barrier variation in the device. Yeah.
Okay. Thank you very much. Thank you, Dr. Yogesh, Dr. Nagaditya, and Dr. Avinash. If you just stay here for 2 minutes, for a token of appreciation is there. Yeah. Have a tea break now, so we'll resume the session after the tea break.
Okay, thanks.